Welcome back to statistics. So we've seen that the sampling distribution of a sample mean tends to have a shape that is roughly normal, and that it gets more and more normal as the sample size increases. What we're going to do in this video is look at a mathematical model for distributions with that kind of shape. These are the normal distributions. Not only are they a mathematical model of these distributions, but they have a theoretical importance too. It turns out that you can prove that if you could get all the x bars into the sampling distribution, then its shape would be exactly normal. And so these distributions are important both practically and theoretically. Let's see what they're all about. So the normal distributions are going to be an idealized curve that describes that familiar shape we see in sampling distributions. So there you see it. It sort of hides all the little spikes and details that are just a result of the fact that we haven't really got all the x bars in our sampling distribution, but it's going to capture the overall shape. That curve is called a normal density curve, and it has a specific form. These are important, as I said, both theoretically and practically, and so we're going to study them sort of in their own right, but keeping in mind that they do describe the shapes of sampling distributions in particular. But I also want to point out that sometimes just data, raw data itself, has a distribution that's described by a normal density curve. So here you see human body temperatures measured, I think there's 10,000 individuals in this data set, and that has a normal shape as well. So how do we use these curves? Well, some of their uses mirror things that we've already done with histograms. So focus for a minute on the left picture in this slide. You see a histogram of Iowa vocabulary scores, and you see also a normal density curve that's approximating that. But just focus on the histogram for a second. There were 947 scores in this data set, and suppose we were interested in the proportion of scores that were less than 6. Those are the scores in the bars that are highlighted in yellow in the graph. What we would do is exactly what we've done before. To find that proportion, we just count up all the measurements that are in those highlighted bars, all the measurements that are less than 6. There turns out to be 287 of those, and we would divide that by 947. And so we would find that the proportion of scores that are less than 6 was 287 divided by 947, or 0.303, or 30.3%. So we've done that before. How could a normal curve give us the same kind of answer? Well, in a normal curve, what we would look at is the area under the curve corresponding to scores that are less than 6. So that's what you see highlighted in the right-hand figure. Notice that that area doesn't exactly match the area under the histogram. There's some overshoot, and then there's some undershoot, and so on. But it turns out that that area is a really good approximation, a really good model for that data. The area under the normal curve to the left of 6 turns out to be 0.293, or 29.3%, and that's very close to the answer we got by just computing with the histogram. Normal distributions have some properties that are constant, that don't change no matter what normal distribution you're looking at. The most important one is that the total area under the curve is 1. As a percentage, that would be 100%. And this just corresponds to the property of a histogram that the total fraction of data in the entire histogram is 100%. So all normal curves are going to have a total area under the curve of 100% or 1. We're going to measure the center of a normal distribution with its mean, which makes total sense since a normal distribution is symmetric and unimodal. So there you see it highlighted. The mean in a normal distribution is going to be right under the peak. So the mean is the x value under the peak, and we'll, as usual, denote this by mu. Since the distribution is symmetric, however, you know that the median is also equal to the mean. So we do have that. The spread of a normal distribution we will measure with the standard deviation, sigma. So this is a little harder to just sort of eyeball on the graph, but I've drawn it here in the figure as that length of that horizontal line you see there. That's our sigma. And once you specify a definite mean, mu, and a definite standard deviation, sigma, you've specified a definite normal distribution. So it's important to realize that there are lots of different normal distributions. Every time you have a mu and a sigma, you have a normal distribution. We use some shorthand to denote the normal distribution with mean mu and standard deviation sigma, and it's just that capital N parentheses mu comma sigma that you have there. So that just stands for the distribution itself. I do want to show you the formula for the actual curve, the normal density curve that gives us this distribution. There you see it. I'm not going to ask you to memorize this by any means. In fact, you really don't have to worry about this much at all in terms of the problems that we'll be doing, because as usual, we'll be using software to do calculations with this curve, including the area calculations. But I think it just wouldn't be a complete statistics course if you didn't see the formula for the normal distribution. And if you've had calculus, or pre-calculus even, you may have seen the number e, which appears in this formula. That's the base of the natural exponential system, and so that is a connection. You also see pi in the formula. That's, of course, the pi from basic geometry, the ratio of a circumference to the diameter of a circle. So it's kind of an interesting formula from that point of view. And again, I think it's just kind of part of a well-rounded education to see that. Again, we won't have to worry too much about that going forward. I do want to go back to this notion that areas under a normal density curve represent proportions of the population. And let's see how that works with a specific example. Suppose that height is normally distributed among U.S. men with a mean of 68 inches and a standard deviation of 2.5 inches. And suppose we were interested in the proportion of men who are at least 6 feet tall. 6 feet is 72 inches. So how could the normal distribution help us find that proportion? Well, you would begin by drawing the normal distribution that's relevant to this problem. And so that would be the normal distribution with mean 68 and standard deviation 2.5. And that's what you see here. I want to point out the way that I've marked off the x-axis here. You notice 68 is there. That's right under the peak. That's the mean of our distribution. But I've marked off the tick marks on the x-axis in units of standard deviation. So standard deviation here is 2.5. So the first tick mark to the right of the mean is 70.5. That's 68 plus 2.5. The second tick mark after that is 70.5 plus 2.5, or 73. So the spacing between the tick marks is our standard deviation. And this is the way you want to mark off these graphs when you draw them too, because it just makes the things go easier downstream. So we'll be doing that pretty consistently. Now let's think about it. What proportion of men are at least 6 feet tall? 6 feet is 72 inches. So that would be represented by the area under the curve corresponding to x values of 72 inches or greater. And that's what I've highlighted here in the curve. The area that is highlighted there would be that proportion of men who are 72 inches or taller. Now, it turns out that that area is 0.0548. So what we can say is that the proportion of men who are at least 6 feet tall in this population is 0.0548, or 5.48%. So when I say proportion, I'll be referring to that area. It'll always be a number between 0 and 1. Oftentimes when we communicate that or report it, we'll convert it into a percentage by just multiplying by 100. Let's take another look at this the same scenario. So suppose instead we were interested in the fraction of men who are less than 5 feet 6 inches tall. Similar kind of process. Start with the relevant normal distribution that's given here. 5 feet 6 inches is 5 times 12, which is 60 plus 6. That's 66 inches. And we're interested in the fraction of men who are less than that. So less than 66 inches. So that's a left tail of the distribution, right? And so that area, the highlighted area here, would represent that proportion. It turns out that that area is 0.2119. So what we can say is that 21.19% of men are less than 5 feet 6 inches tall. Again, areas under the curve represent proportions of the population. One more quick example. Suppose we were interested in the proportion of men who were between 5 feet 6 inches and 6 feet tall. So again, we draw our normal distribution, and now we're looking for the area between 5 feet 6 inches, or 66 inches, and 6 feet, or 72 inches. So there you see that area highlighted. That area turns out to be 0.7334. And so 73.34% of men in this population are between 5 feet 6 and 6 feet tall. So areas under the curve represent proportions of the population. Now, you may be curious as to how those areas, which sort of just appeared magically in the slideshow, are actually calculated. Well, our SALT tool can help us do that. It has a normal distribution calculator that is very handy for these kinds of things. So let me pull that up and let's check it out. So here I'm in SALT. If you look above here, where I'm at is in the Distribution Calculators tab. So that's right to the right of the Charts and Graphs tab that we have been using. The distribution that comes up when you initially click on that tab has a mean of 0 and a standard deviation of 1. That's actually an important distribution. It's called the standard normal distribution when the mean is 0 and the standard deviation is 1. You see those two numbers right up here in this dialog box. But that's not quite the one we need here. We need a mean of 68 inches, so I'm just going to type that into the box here, and a standard deviation of 2.5 inches. And so I type that into the box, and now you see the normal distribution that we need. Notice that SALT has marked off the x-axis just as we did in the slides in units of standard deviation. Okay. So suppose I was interested in the proportion of men whose height is at least 5 feet 6 inches. That's 66 inches. And when I say at least 66 inches, that means 66 inches or greater. So I have to realize the first thing is that I'm interested in a right tail of the distribution. And so you go up here into the upper right part of the graph and you click on right tail. Now we want the right tail beginning at 66 inches. So when I go over here to the dialog box and under probability, I replace the number they have there with just 66 inches. And there we have the probability of heights that are 66 inches or greater. Turns out to be 0.78814, and you see the area shaded here. And so that's a quick and easy way to make these calculations, and I want you to use SALT in making the calculations for the homeworks and even for some of the problems on our module tests. That's a pretty handy little tool. What if you were interested in the proportion of the population that, say, less than 62 inches? So if I'm saying less than 62 inches, that means 62 inches or lower. That's a left tail of the distribution. And then I go back over here and under my probability tab and I say less than 62 inches, and you see that area highlighted right here, and the answer you're looking for is in the box here, 0.0082. So that it would be 0.82%. So less than 1% of men in this population have a height of less than 62 inches. Finally, you can do the between kind of calculations as well. What if I were interested in the probability that someone's height is between, let's say, 62 inches and 73 inches? So now go over here and select the between button, and we want between 62 and 73 inches, and we see the area shaded here, and we see the proportion as 0.96905. So about almost 97%, 96.905% of individuals are between 62 and 73 inches tall. So that's our initial look at the normal distribution and our calculator on SALT that'll help us make some of these area calculations. The big thing to remember here is that areas under the curve correspond to proportions of the population. And we'll be using this fact in multiple different ways going forward. So I hope this helps. Let me know if you have questions, and we'll see you again real soon. Y'all take care.